Good morning, everyone. Thank you for taking time out of your busy schedules to attend our water wastewater webinar series. Today's webinar is Improving Efficiency While Managing Infrastructure Assets. My name is Nick Amico, and I'm going to be your host for today. Sitting with me is our presenter, Mr. Ben Stevens. Ben, how are you today?
Good, Nick. Thank you.
A quick introduction on Ben. He's a manager of engineering services. He has a degree in marine engineering from Mass Maritime Academy. He has been with Chesson for over 10 years and specializes in rotating equipment. His effort focuses on reliability and energy efficiency. He is heavily active in the Hydraulic Institute and Pump Systems Optimization Program and is certified in maintenance and reliability professional. So, just a few housekeeping rules. Please feel free to ask questions if you have them. Type in the questions in the chat box on the left-hand side of your screen. We'll be answering all questions at the end of today's presentations. We have a lot to cover today, so sit back, relax, and enjoy the presentation. Ben, the floor is yours.
All right, thanks a lot, Nick. All right, just a precursor. Try to distill down the title a little bit. Improving efficiency while managing infrastructure assets is a mouthful. What we're going to focus on today primarily is pumps and systems, and more specifically centrifugal pumps. So we live in a world of pumps. Department of Energy estimates that electric motors consume 2/3 of U.S. industrial electricity. Of that, 27% of these motors are coupled to a pump. In 2015, the industrial sector consumed 800 million megawatt hours of electricity at a total cost of over $56 billion. And what that boils down to is about $10 billion worth of energy is going into our pumps. So if we're looking for ways to save energy and save money, looking at pumps might be a good place to start. So pumping efficiency. What are the pumps doing with all this energy? And this was a study that was conducted by the Finnish Technical Research Center. What they did was they evaluated about 1,700 pumps at 20 different process plants. Their findings were that the efficiency average was below 40%. Over 10% of the pumps were running below 10% efficiency. Now, to put this in perspective for you, a pump typically gets spec'd out when it's new to operate between 80 and 90% efficiency, depending on the design. So some of the major factors that were affecting the efficiency of these pumps. Pumps were throttled. Pumps were oversized. Those two tend to go hand in hand. Or simply, the pumps were just worn out. So we're going to take a look at the typical 20-year life cycle cost of a 75 horsepower pump. It's a good average size that we see a lot in the water and wastewater industry. So starting at the top of this pie chart, we have the green piece, which is the initial cost or the acquisition cost. It's about 9% total life cycle. Installation, about 8%. Go on to the maintenance cost. We're up to about 28%. And finally, the largest piece of the pie, the operating costs, total 55% of the life cycle cost. This is primarily your energy going into the pump. All right? So when we look at how we size our equipment, how we run our equipment, how we're going to mitigate our undue costs, we really want to focus on the biggest piece of this pie, and that would be the operating costs. So now we're going to talk about a typical single-line pump curve. I know that there's people on the webcast here who probably are very familiar with curves, but we're going to just go through the basic pieces of this. So you have in front of you a graph with multiple y-axes, and across the x-axis is the flow or the capacity of the pump. This one's labeled as US gallons per minute. So the first curve that we have, and I'm going to try and use my on-screen arrow here, is this black curve. Okay, and this is the head flow curve. This is the head or the pressure differential across the pump that is developed corresponding to the flow rate of the pump. Next curve we're going to talk about is this red curve down here. This is the power curve, or the brake horsepower curve of the driver. And the driver might be an electric motor, could be an internal combustion engine, could be a windmill, I don't know. But this is the brake horsepower that the motor must produce for the corresponding flow rate. Next curve is the green curve here. This is the efficiency curve. This is the ratio of brake horsepower to what is called water horsepower. Okay, this is the hydraulic work that the pump performs. Okay, and what you see here is the efficiency curve actually has a peak. So depending on where the pump is running along its head flow curve, the efficiency varies. And we want to size our pumps so they operate around this peak. The peak is commonly referred to as BEP, or the best efficiency point. And lastly, but not leastly, is the blue curve. This is MPSH-R. MPSH-R stands for net positive suction head required. In simplest terms, this is the pressure at the suction of the pump required to prevent cavitation. Cavitation will damage the pump. And you can see as the flow rate of the pump increases, we require more pressure at the suction of the pump to prevent cavitation. Now this is not to be confused with a similar term, which is MPSH-A. The A stands for available. What we have available must always be greater than what is required. I neglected to mention at the beginning of the presentation here that if there are any questions as we're going along here, feel free to type them into the dialog box and we'll address those at the end of the presentation. So we discussed the pump curve a little bit. Now here's a pump curve that shows the effects of where we operate on the curve on the reliability of the pump. All right, and there's a lot going on here. So if you look at the right-hand side of this graph, we see the reliability of the pump. The top of it being maximum MTBF, or mean time between failure. This is optimal condition. This is how long you want your pump to last. And as we migrate across the curve, we see that we lose reliability. As we get further away from BEP, we reduce the life of the pump. And you can see some of the text in here, some of the symptoms of running away from BEP. When we run out on the curve, we get cavitation in the pump. We're going to reduce our bearing life and our seal life. When we start to run in on the curve, or the left end of the curve, we begin to get internal recirculation in the pump. And we get far enough in, this internal recirculation can result in cavitation as well. We're also going to increase vibration, which will reduce bearing life and seal life as well. So the key takeaway to this graph is we want to be running in the sweet spot, which is BEP. An efficient pump is a reliable pump. All right, so we covered pump curves. We talked briefly about system curves as well. When I talk about system curves, we're using the same graph. We have head on the y-axis and flow on the x-axis. So our first example will be a static dominated system. All right, and you can see that the shape is actually kind of opposite to a pump curve. And what this is illustrating is that as we increase flow through a system, we have to overcome increased head loss. So we need to put more pressure into the system to create more flow. In a static dominated system, most of the head that we're producing is to overcome some kind of pressure differential or elevation difference in the system. All right? The remaining shape of the curve is head loss that is induced by frictional losses in the system. Now this is a friction dominated curve. You can see that there really is no static head in it. It crosses the graph at the origin. And all the losses in this type of system are induced by friction. Okay? Essentially, the pump is is pumping back to itself. There is no elevation or pressure differential to overcome. So a couple examples of these two different types of systems. Static dominated system might be an influent pump in wastewater. A pump is taking draw off of a wet well and it's pumping into an aeration basin. All right, it's not a long distance, but it does have to overcome a change in elevation. That would be a static dominated system. A good example of a friction dominated system might be closed loop cooling. Essentially, the pump is pumping through the system, the pipes, the fittings, the heat exchangers, and it's returning the fluid back to itself on the suction side. Okay? Good example of a friction dominated system. So previously we mentioned that the pump can operate somewhere along its head flow curve, anywhere along its head flow curve. But the question is, where does it operate? Well, we got to think about the system. The system is what determines where the pump operates. So we overlay the system curve on the pump curve. In this case, we have a flat curve. Where those two intersect is where that pump will operate. And we can read the corresponding head and flow. Now imagine we put that same pump into a different system, in this case, a friction-dominated system. It's going to have a different operating point. And what's important to realize here is that the same pump inserted in two different systems will give you drastically different operating points. So you always beware of what you read on the nameplate. Very rarely will the pump actually be doing what the nameplate says it's doing. Okay, so this is pumps and systems is a very broad and deep topic. I'm not going to be able to get into all the details in a 45-minute session, but this is something that I thought was worth noting. There's something called specific speed, and it is a characteristic of pump designs that includes the head, the flow, and the rotational speed. And there's a formula for specific speed, which is a unitless number. And what this graph is showing us is along the x-axis we have the spectrum of specific speed from 0 up to 7,000. And there's different types of pumps that fall into this spectrum. We have radial flow pumps, we have split case pumps, end suction pumps. They all fall somewhere along this spectrum. And what it's showing us is where are the losses in these pumps? What causes a pump to not be 100% efficient? So the first two bars on the top, the yellow and the orange, these are, for all intents and purposes, are irrecoverable losses. These are mechanical losses and are impeller losses. Okay, this is rolling resistance, this is bearings. There's not much we can do to recover those losses aside from more efficient mechanical equipment. Moving on to sections 3 and 4, we have our disc friction losses and our leakage losses. Okay, this is the effect of wear, the surface finish in the pump, the wear rings. These are losses that can be mitigated. Next two sections, 5A and 5B, these are losses more attributed to the type of pump that you have. We see vertical pumps and double suction pumps suffer from these losses. And then everything that's left over in the green area is the output of the pump. So what you can see is as we go across the spectrum of specific speed, we can see typically the max efficiency that we're going to see from that type of pump. And somewhere between 2,000 and 3,000 are going to be our most efficient pumps. So what are the effects of deterioration on a pump performance curve? So as I mentioned before, we overlay the system curve and the pump curve to find out what the operating point is. So here is the head flow curve for a new pump. Here's the power curve for the new pump and the efficiency curve for the new pump. And here's the operating point. All right, and we draw a vertical line down through all those curves. We can determine what the power is, what the efficiency is. And what happens when this pump gets worn out? We have new curves, okay? And you can see the head flow curve has been reduced. The power curve is actually increased. It's taking more power to do the same amount of work. And obviously it goes without saying that our efficiency has been reduced. So we slide down to the new pump curve. We're still on the existing system curve. The system has not changed. We draw a vertical line down there. We can determine what the new power requirement is and what the new efficiency is. And we can see what the loss of capacity is. So I drew some new curves on the last slide. Well, how do we do that? How do we determine what the new curve looks like when a pump is worn out? Well, this is something that we call a wire-to-water efficiency test, and this is something that can be performed in the field on your equipment while it's running. So there's a couple elements you need to gather out in the field. First is the power that the motor is drawing. So we use a power logger in this case, and we can determine voltage, amperage, power factor, and thus kW. Next data point that we're going to gather is total dynamic head. We need suction pressure and discharge pressure for this. This is the pressure developed across the pump. And the last important piece is the flow going through the pump. And with these elements, we can determine the water horsepower of the pump, the brake horsepower of the driver, and essentially the hydraulic efficiency. So we'll take a look at a case study now. This was an oversized pump. It was oversized during the design phase of the project. And here's what happened. The process required 4,000 gallons per minute in flow. However, operations requested 4,600 gallons per minute for margin of safety. They anticipated maybe there would be more demand at some point in the future. So the junior project engineer calculated the head loss to be 39 feet at 4,600 gallons per minute. He turned his work into the senior engineer, who then added 7 feet to the calculated head loss because he couldn't trust the junior engineer. So now we have a pump spec'd out. It's going to be sized for 4,600 gallons per minute, 46 feet of head. The maximum efficiency they could get at that operating point was 82%. So the pump is ordered. Pump arrives, it's installed. However, the process still only requires 4,000 gallons per minute. So what do? They throttle the pump. And when they throttle that pump, they push it back on its curve. The pump is now creating more pressure than it otherwise would have needed to. And it's also lost efficiency, now operating at 77%. So what is the cost of throttling an oversized pump? Well, it's real simple. We can calculate the brake horsepower in both scenarios. First scenario, 4,000 gallons per minute, 50 feet of head. This is what they ended up with at 77% efficiency. Requires 65.6 brake horsepower. Now, had they sized the pump appropriately at 4,000 gallons per minute and 39 feet of head, operating at 82% efficiency, they would have only required 48 brake horsepower. So we calculate the difference between those two. We assume that the pump is operating at 4,000 hours per year. They splurged for a premium efficiency motor, 95% mechanical efficiency, and we can determine the difference. It's roughly 55,000 kilowatt hours per year. We apply a typical electric rate to that, about 12 cents per kilowatt hour. It can be more expensive in the Northeast. It can be less expensive down south. It varies. But that's about $6,600 per year. It's the incremental cost of operating this pump in a throttled condition every year. So what's the solution to this problem? Well, they could put a smaller pump in there, of course, but they already spent all that money on the larger pump. So we opted to install a VFD. Once the VFD was installed, we reduced the speed to 80%. And you can see that the pump head flow curve has been corrected down for the 80% speed. And what's happened is we've slid further down the system curve. We have a new operating point. Now that new operating point is going to be somewhere less than the required 4,000 gallons per minute. So we need to take one more step. We open the throttle valve. What happens when we open the throttle valve is it flattens out the system curve, and we returned again to our 4,000 gallon per minute requirement. The result was that we reduced the head across the pump by 11 feet, and we reduced the brake horsepower by 18. Total project cost was $10,000. The incremental cost again was $6,600 per year, so the payback period was about 18 months. It's a no-brainer. Look at another case study. You wastewater and water guys should be familiar with these pumps. I'm sure you all have pumps that look similar to these when they come out of service. It's not pretty. This is rust, this is corrosion, this is tuberculation, this is erosion. This is what happens to cast iron pumps. They don't like water. The suspect, wastewater. We have an Alice Chalmers 12 by 12 by 15. It's a 75 horsepower pump. So operations knew that the pump had lost performance, but they wanted to quantify the cost of this loss. They also knew that the pump had issues because it was making a terrible racket coming from the casing. So they teamed up with us to take a look at the performance of the pump. So we did our wire-to-water efficiency test. All right, and here are the results of the assessment graphically. So the first point I want to talk about is the nameplate operating point. 5,000 gallons per minute, 52 feet of head. Now you'll notice at this point, it's just kind of hanging out by itself, suspended in midair. It's not on the pump curve, it's not on the system curve. And as we know from our earlier discussion, the pump cannot operate there. The pump must operate somewhere along its system curve. It must also operate somewhere along its pump curve. This is neither. Next point. This is the OEM operating point, the intersection of the two curves. What that was calculated at was roughly 4,200 gallons per minute, 51 feet of head. This is what the pump predictably would do in a new condition from the manufacturer. And the final point is what we measured. This is the measured operating point, roughly 2,000 gallons per minute, producing about 20 feet of head. So let's break down the numbers and see what that looks like. This pump had lost 32 feet of head. It was pumping at less than half of its original capacity, from 4,200 down to 2,000. It was actually consuming more power than it would have in a like new condition, 2.4 kW. The efficiency had dropped from 83.5 down to 14.6. And of course, with the reduced capacity, the pump had to run longer. So we went from about 1,500 hours to the pump was now running 3,000 hours per year to produce the same amount of work. We look at that in energy. It's an incremental 100,000 kilowatt hours per year. And what's that costing us? About $11,500 per year. The incremental cost of operating this pump in this condition. So it was decided to pull the pump out of service. This is what we realized upon teardown and inspection. Now this is the cut water right here and right here. Okay? That line is supposed to continue straight across. There's not supposed to be a hole in the cut water right here. Alright, so this was primarily what was affecting this pump. Among other things, the inside of the casing was worn, it was corroded, the wear rings had eroded away. So it was decided that this pump had another life left in it. So what we ended up doing was rebuilding the internals with a high build epoxy. We restored the cut water geometry, and then we applied a high efficiency, low friction ceramic reinforced coating to the internals of the pump. The coating will resist the corrosion and erosion effects commonly experienced in water and wastewater, And it also reduced the surface energy, increasing the hydraulic efficiency of this pump. Lastly, the wear rings were renewed, bearings and seals were replaced, the pump was dynamically balanced, it was reinstalled and laser aligned. Now this is a term that I feel I coined. I'm not positive on that, but this is what I call the time value of efficiency. And what this graph is showing us is typically over a 5 to 10 year span, our pumps are going to lose about 10 to 15% efficiency. And honestly, from what I've seen, this is a conservative number. So we're experiencing lost efficiency, increased operating costs, increased runtime, increased maintenance costs. It's all costing us money unnecessarily. So getting back to the pump that we restored in the wastewater, total project cost to restore that pump was $15,000. You remember the incremental cost was about $11,500 per year. It's yielded a 15-month payback. Again, another no-brainer. Additionally, protecting the asset with the internal coatings is going to continue to protect it against the wear and will continue to pay dividends. So I want to take a look at a study here that was performed in New York. This is a report that is available out on the internet for anyone to go out and find. And the group is called NYSERDA, which stands for the New York State Energy Research and Development Authority. So what they did was they teamed up with the Monroe County Water Authority to look at some pumps and the benefits of coatings on these pumps. They had about 20 pumps ranging from 30 horsepower to over 1,700 horsepower, and they were meticulous about this study. All right, so what they started out by doing was conducting a wire-to-water efficiency test on all of their equipment so that they could get a baseline. And then they started pulling these pumps out one by one and performing mechanical refurbishments on them. And by that I mean wear rings, bearings, seals, etc. Then they would reinstall those pumps and perform another wire-to-water efficiency test on it. And what you see on this graph is a couple different colors in each bar. And now the lower portion of each bar, the light green color, was the efficiency gains that they saw during this first step in the process, the mechanical refurbishment. Next, they decided, pull the pump back out of service, we'll sandblast the internals, and we'll apply coatings to it. They did that, then they reinstalled the pump, measured the efficiency again. And that's the top portion of these bars, the dark green portion. And on a few of them, they actually pulled it out a third time, and they applied coatings to the impeller. That's the red portion on these bars. And what they saw was, on average, they were getting about 5%, 6% from the mechanical refurbishment. They were getting another 5, 6, 7% from the application of the coatings. And then they were getting 1 to 2% by coating the impeller. So these were some pictures that were provided to me by one of the lead engineers in this study. His name was Paul Mayer. And this was his pump before he sandblasted and coated it. And just to give you guys an idea, this is fresh water. This is the water that you brush your teeth with. This is the water that you shower in. It's not too nice looking, is it? That's a little better. Not perfect, but better. So this is what it looked like after they sandblasted and coated the pumps. It's a stark difference. So they asked themselves, well, the coatings are great. We know that they've restored our efficiency, but how long are they going to last? So 4 years later, they said, let's pull the pump out and do an endurance test on it. So the first picture on your left here is what it looked like when they broke the case open. And they said, oh, it's all rusty again, the coating failed. And they said, well, hold on a second, let's get a Scotch-Brite pad and clean it up. They cleaned it up, looked like a new pump again. Coatings were fine 4 years later. Said, great, let's put it back into service. 9 years later, I think it's time to test the pump again. So they pulled it out, looked at it, said it's rusty again, but the coating's still there. Let's get our Scotch-Brite pad, check it out. Clean it up. Not perfect, but it's pretty close. This is 9 years of service. That pump looks good. Now, I don't know many cast iron pumps that look like that after 9 years of service. I think this is a testament to the benefits of the coating. So in conclusion, and these are NYSERDA's words and not mine, what they decided was that routine field testing of pumps is essential. Pump sandblasting and coating should be part of any pump refurbishment program. In this particular study, at least 50% of the improvement in pump performance was due to sandblasting and coating. And lastly, no one in their right mind would use unlined ductile iron pipe. Perhaps it's time to consider the wisdom of using unlined pumps as well. So we talked about the efficiency tests that NYSERDA performed. This is the assessment of the pumps. So what are some of the benefits? Obviously, we're looking for energy savings, but we have peripheral benefits as well. Higher reliability, increased productivity, less wear and tear on our equipment. We're going to reduce our maintenance costs. We're going to reduce production losses. We're going to increase the uptime of the equipment, increase the capacity utilization, and ultimately, when we save energy, we're going to reduce our environmental impact. So when we're performing assessments, we really want to kind of form a team. And we have all these different people at our plants and facilities. We have purchasing groups. They're interested in how much the asset costs. We have engineers. They want to know how it works. Operators are interested in, is it reliable? How much does it cost to run? And lastly, maintenance. Is it easy to repair and maintain? So each group believes it makes a rational case for its thinking, and they do. Each one of their perspectives should be considered. All right? We have to keep in mind that we're evaluating a total system. All right? And we need to look at the system and not just the pump. We're making a business case to improve our systems. Again, making the business case for optimization, increasing efficiency, reducing operating costs, increased reliability, lowering the life cycle cost, increasing our customer value, and making sure that we have a sustainable organization. Here's a couple publications that I personally use to help me go through my daily activities. The first one on your left there is the ASME EA2, which is an energy assessment for pumping systems. Some of the topics discussed are scope, definition, references, organizing your assessment, conducting your assessment, analyzing the data, and lastly, your reporting and documentation. This is a very similar standard to the ISO 14414 Pump System Energy Assessment. Both available to you. So what is my process? I pre-screen my equipment. I make a list of everything, and I figure out where the best opportunities are. Step one. Once I've identified the equipment that I want to look at, I'll conduct a pump and system assessment. After the assessment, I will have identified opportunities for improvement. So I need to come up with an action plan and implement it. Now, what are some of the elements of this action plan? It could be repair and refurbishment. I don't think it's any secret that I'm an advocate for application of coatings. The pump may not have been properly sized, so it may actually mean equipment replacement. And we may even look into control scheme for the system. The final step is to begin the process again. Go back to our pre-screen list and pick the next system in line. So some key points to improve your pumping systems: follow the plan. Create a partnership between production, management, purchasing. Find out what each one of them considers important. Begin with something small and involve all these stakeholders. Document everything you do. If you don't have the in-house expertise, partner with appropriate pump system experts. Measure and report the impact of system changes in terms that are important to management and production. In other words, show them the money. Use your life cycle cost analysis that we discussed. And again, repeat the process. So that's what we have today. And we're going to open the floor up to questions. I see we didn't get any questions during the presentation. We did receive a couple questions ahead of time. I'm going to go through these, and while I'm doing that, feel free to type into the dialog box on the left there, and I'll address any questions that we had during the presentation. So the first question I have here, I don't have my pump curves. Where can I go get them? Well, the simple answer is the manufacturer. Generally speaking, you can get most book curves from the manufacturer's website nowadays. And when I say book curves, there's two different curves. There's the book curve, which is kind of generic. It's going to apply to any pump in that model and size that the manufacturer would sell. The other type of curve that they might have is a certified curve. This is when you purchase a pump, they physically take the pump that they're selling you, put it on a stand, test it, and provide you that data with the pump. Now, some pumps aren't in production anymore, or actually the manufacturer might have gone out of business. But it doesn't mean that somebody else doesn't own the patents for those pumps. So with some digging around, you will certainly be able to find curves for 90% of the equipment out there. If all else fails, you can always work with a pump professional to create a curve for your equipment through some field testing. The next question here we have, my pump is running off of its curve. Why is that? Well, first thing I'm going to dispel is that pumps cannot run off their curve. They can run out on their curve, they can run in on their curve, or the curve may no longer resemble the original manufacturer's data. Rest assured, though, that pump is operating on its curve. Now, if the pump is running outside of the manufacturer's preferred or allowable operating region, further investigation may be necessary. Could be a problem with the system controls, or the pump may not be sized correctly. In any case, operating the pump at these extreme conditions will surely result in wasted energy and eventually failure. Next question. I don't have instrumentation on my pumps, so how do I know where it's running? Well, there's no crystal ball that's going to tell you where your pump is running. I wish there was. It would make my job a lot easier. Facilities that have poor instrumentation have approached me before because they simply noticed their energy use was increased, or their equipment now takes 5 hours to do what used to take 3 hours. These are your symptoms of issues, but they are not a substitute for a comprehensive assessment of the equipment. For this, you will need a minimum instrumentation as described in the water efficiency slide. Again, pressures, flows, and power. Next question. Why does my pump cavitate? Well, that's a really broad question. There's many reasons. There are also different types of cavitation. There's even cavitation that's occurrences not obvious to us, known as incipient cavitation. Among the more common causes of cavitation, though, are operating at either extreme end of the pump curve. When operating to the left end of the curve, the pump experiences recirculation, which can be evidenced by pitting and erosion on the impeller vane tips. This is due to high discharge head and low flow. When operating to the right end of the curve, or in a run-out condition, the pump experiences cavitation on the suction side of the impeller and in the impeller eye. This is generally the result of insufficient suction head. There are several ways to alleviate cavitation, but understand that this is a system issue and not a pump issue. The pump only operates where the system allows it to. Last question I have. Is there a way to mitigate the corrosion-erosion effect on pump internals? So as discussed in a couple of the case studies, internal coatings can provide excellent protection against the effects of corrosion and erosion. Additionally, operating a pump in its preferred operating region will minimize cavitation and thus pitting and erosion. When applying internal coatings, it is important to seek professional advice on the application and the product to be used to ensure compatibility. Proper surface preparation is paramount when it comes to using coatings. Over 80% of coating failures are a result of improper surface prep and application technique. So those are the questions that we had from before the webinar. And I see we have some comments popping up in the dialog box here, so let's address those real quick. So from Charlie and Antonio, we have running off the curb might have a different impeller installed. Measuring portable meters can be bought or rented or flow for electricity. Okay, so let's address the first part of their question. Running off the curb might have different impeller installed. So if the pump is running in an undesirable part of its curve, i.e. it's out on its curve or it's in on its curve, we could change the impeller. We could trim the impeller, or maybe we needed a larger impeller to begin with. That would change where the pump is running on the curve, because the system should stay the same, and when we change the impeller, the pump curve is going to change. All right, it's either going to expand or it's going to contract, and we'll operate at a different point. So yes, that's an excellent point that changing the impeller can change that. Measuring, I'm not sure exactly what the question is, but we own our own equipment because we do assessments pretty often. But I know that flow meters, power meters, they can all be rented on a weekly or even monthly basis if you just want to get into your own equipment and perform some water efficiency tests. Next question we have from Alan. Do you have guidance on optimal ranges of head and capacity with respect to efficiency for HSC pumps? I'm not sure I can answer that question right now in the webinar. I will say, though, that depending on the type of pump that you have, whether it's an ANSI-style pump or an API-style pump, I'm going to refer you back to the slide that we had that was produced by Paul Barringer, the Barringer curve, where the effect of operating away from your best efficiency point, we have ranges there, and I believe it was about 10% back from BEP and 5% out from BEP are about the range you want on an ANSI-style pump before you start losing reliability. On an API pump, that range is probably wider because they're a little more robust in design. They can take a little more abuse. Answer Paul's questions. Can the slides be shared or made public? So yeah, Paul, the presentation is going to be shared next week. The webcast has been recorded. It will be available on a link to YouTube that you'll get in the package next week. And one other thing that I wanted to mention was if there was anything that wasn't addressed in the webinar, or there's maybe a more in-depth question that someone didn't ask right now, my contact information, Nick's contact information, and Paul Keogh's contact information will be available to you guys to reach out to us and talk about this. So with that, if we don't have any more questions, I'm going to turn the floor back over to Nick.
Thanks, Ben. Great job. All right, folks, thank you very much for coming to today's presentation. We greatly appreciate it. If you want to take a quick look at the chat box, I actually just posted a link to a survey that we created. If you could just take a few minutes to just go through the survey, we would greatly appreciate it. It's not only going to help us to further enhance our presentations, but to hear your feedback, it's always great to hear from our listeners. So with that being said, we'll leave it up for a few minutes. Also, as Ben also already addressed, we will be sending out a copy of the presentation and the link to the webinar next week. Also, please be sure to join us in the next part of our webinar series on August 5th. We'll be leaving this link up for you guys for a few minutes. I hope everyone has a great rest of their day, a fantastic weekend, and happy Independence Day. Thanks a lot.